Okay, so welcome everybody to our inaugural Optimization in Oslo seminar. I'm very happy that we were able to get Karl Kunisch from the University of Graz and Radon Institute in Linz to be our very first speaker. I don't think Professor Kunisch needs a lot of introduction. I think many of you are familiar with his papers. He's written 350 papers, co-authored 350 papers, and has several monographs. He's one of the Reed Prize and also a few years ago an ERC Advanced Grant. So I think he should be quite well known to most of you. And today he's going to talk about solution concepts for optimal feedback control of nonlinear differential equations. So Karl, please.
Thank you very much, Thomas. Thanks for joining to this seminar. Thanks for the honor of being a speaker here, being actually the first speaker. If difficulties arise, please, of technological nature, for example, also in this case, please feel free to interrupt. Of course, I am sorry that I'm not there in person, but that's in part due to simply my time schedule and also to Corona. To get towards the topic of today's talk, little of a historic component. Optimal control for differential equations is of course an old subject. Optimal control subject to PDEs has been taken up in the 70s and 80s of the last century. And towards the 90s, and a lot of numerical techniques have also been studied to be developed. Optimal control for PDEs really needs good algorithms, good computing power, which, for example, in the context of Navier-Stokes, wouldn't have been available in the 70s. So, but around 80, 90, we started to work on it. We was several groups throughout the world, and Graz was one of them which got involved, and Thomas helped in this context as well, especially in the context of what we call open loop control. I'm going to explain this in a moment. Very little has been done for feedback or closed loop control. This was a topic of my ERC grant proposal. It was the high risk component, and at that time we really didn't know, I especially didn't know how far we would be able to go. And we have now several contributions. Many people around the world are working in these directions, and some of my collaborators are mentioned here on the first slide. I work basically at the University of Graz, but I also have a joint appointment at the Johann Radon Institute of the Austrian Academy of Sciences, which is located in Linz, a city of 200,000 in the north of Austria, between, let's say, Salzburg and Vienna, the two well-known hotspots. I'm interested in the situation where we have a dynamical system y dot equal f of y. At the moment, I don't insist on it, whether it's an ODE or PDE. So you have a model for the, if you wish, pandemia. But then we have an additional feature which we can act on the system by means of a control, U of t, vaccination. And of course, we want to do this in an intelligent manner. Of course, engineers have good a priori knowledge, so they may know what to do anyway, and they choose from their knowledge a reasonable, pragmatic control. And the system will react to it and have a trajectory depending on the control chosen. A step further, next step would be to do this in some sense in an optimal manner. Now the control PDE arises as a constraint under a cost functional, which involves the state of the dynamical system, and a cost for the control. Gamma is positive. One of the main topics in optimal control is really stabilization. You want to stabilize the trajectory to a steady state, which was normalized to be the origin here. So f at 0 is 0. L, you may think of it as just a quadratic cost. So the origin definitely is the solution, and we want to stabilize this system. Okay, the way it is stated here, you may say, I immediately know how to do that. I have a good optimizer. I discretize this constraint here. I use the best of the optimizers that's available to me. And I simply consider this as an optimization problem, which I can solve. No problem. And then in this framework, there are two approaches. The first approach would be, given u, I calculate y of u, I stick it into the cost, and then maybe I compute the gradient or a Newton step, and I iterate. That's the reduced formulation. Alternatively, I can look at this functional in the two variables, state and control, and then the equation arises as an equality constraint here. Fine. And then maybe you have a new class of algorithms, and you choose between the two the best you think, the algorithm which you think is the best fit. I want to go a step further. What I have explained to you was the open loop formulation of control problems. You want to control the pandemia, you compute offline the control, and then you apply the control, and hopefully you go below threshold in the number of infected species. But maybe we want to do something different. We want to look at the population and choose our control as a function of the state. In a cartoon, what I did so far, I have a control system, I stick into the nonlinear dynamics, maybe I optimize and I get an output. Once I have computed that, if somebody acts on the system, or if I have made a mistake in the initial condition or something, I have to start from the beginning for a new U. The closed loop world is a different one. I assume that I can observe my state, I get an output, I'm looking for a feedback operator, and stick this K into the dynamics. So I'm looking for a feedback operator. Okay, so what I have done so far is, first I have simply a control without optimization. Then maybe I have an optimal open loop control. Then I'm going to the feedback one, and maybe an optimal feedback. Those are the issues. I am going after the K star. Okay, since I'm not assuming that all of you are familiar with closed loop control, let's start with a simple problem. I have a linear dynamical system. A is a matrix, in case we are considering an ODE, or the ordinary differential equation, or you may think of the Laplacian if you want to think of diffusion processes, or a linear dynamic, a linear operator. And I have a quadratic cost. Then, under some technical assumption, we can guarantee that this Riccati equation for the unknown pi, involving the right-hand side, the control operator B, and the observation operator, that this Riccati equation has a solution. I take, which is a symmetric, positive definite matrix in the finite dimensional case. I utilize this, I act on the state, I act with B transpose. I choose this as my U. I take this U star, stick it in on the place of U into the dynamical system. And what I have done is I close the loop. This is the optimally controlled dynamical system. in a feedback form. I have closed the loop. A tremendous amount of work has gone into optimal code design for this Riccati equation, simply because this is really one of the a main tool in engineering, in electrical engineering practice, for example. It is so useful and so powerful that also in the situation that A is nonlinear, people linearize around the trajectory, around the steady state, around the trajectory of interest. They linearize. They look at the linearized system, which is then, of course, time dependent because of the linearization. And for the linearized system, they do a Riccati feedback synthesis. And this is very effective in practice, and people have proved that this is justified in theoretically, at least locally, around a neighborhood of the origin in this case. That's the linear world. And now we go to the nonlinear one. So I have the same functional. You may still think of y, Ly is still of y squared. F at 0 is 0, but now f is nonlinear. I want to explain how we get to the analog of the linear quadratic case. For this purpose, I introduce the optimal value function, which is the function which assigns the cost, the optimal cost j, corresponding to the initial condition x. So at this moment, unless you already know in which direction I'm going, this may look at as, this is not well motivated yet. But later on, we will use as our x, the state of this system, wherever it happens to be at time t. So later on, x is going to be y of t. But for the moment, this is the value function. Okay, this value function as the initial condition varies, satisfies what's called the Hamilton-Jacobi-Bellman equation. At the moment, it's a little difficult because even the equation has a minimization involved. But still, once the minimization is done, it's a function of x. If you look at the right-hand side, you see it here. You see the running cost, Ly plus gamma u squared. And this n-valued or the Hilbert space valued image of the right-hand side is pre-multiplied by the transpose of the gradient of the unknown v. This is the v from up here. So this value function is a function of the initial condition, satisfies this nonlinear hyperbolic equation. The value, if you start x at 0, then of course the value is 0. And a little bit of deliberation, we also find the boundary condition. This value function is positive away from the origin. So at the origin is 0. So assuming it's the value function is differentiable, we have the gradient vanished. So we have, if you wish, boundary conditions. Of course, the value function in general is not C1. So we need to introduce viscosity solutions a la Pierre-Louis-Lyons, for example. But I'm not going to go in this direction. What I want to stress already at this moment is that this hyperbolic equation, in addition to problems of first order hyperbolic equations that we know about, its dimension is the dimension of x, which is the dimension of the system here. So if you're thinking of an ODE in dimension 15, this is a PDE in dimension 15. If you're thinking of a PDE, that's an operator theoretic first order hyperbolic equation. So this is a tremendous obstacle. In the specific situation that the admissible set of controls is all of the space, so if there are no control constraints, then we can minimize by hand with respect to U. So if affine, this is affine in U, this is quadratic, so the necessary and sufficient condition, this one, we can plug U star into the equation and we get a new formula for the Hamilton-Jacobi-Bellman equation, or in this situation of unconstrained control. So now we are interested in solving this equation for V, or gradient of V. Once we have it, if we find it, we again stick it into the dynamical system. This U star, you stick it in here, and you have closed the loop with optimal control. If we only have V, then we have a closed loop formula. The trouble is that, and the derivation of this HGB equation is not too difficult by fact. That at least the ad hoc choice. You just you use the Bellman principle. So instead of going over the infinite horizon in time, you go from 0 to some tau, and then you continue from tau to infinity. So this equality is known as the Bellman principle. In the next step, you take V of x to the right-hand side, so I have this minus V of x. I divide by tau, and now in the next step, you let tau go to 0. So you see L of y, this is my L of x, at the initial condition is here, then I have gamma 1/2 u, and then you need to work a little bit, and then we have it. So the derivation, the formal derivation of the HGB equation is very simple. And the rigorous one, yes, then you get a Fields medal for it. That's what happened to Pierre Louis. I want to stress that behind that is the curse of dimensionality, already mentioned in 61 by Richard Bellman. What cast the pole of our victory? The curse of dimensionality, a malediction that has plagued the scientists from the early days. So already between 60 and 2020 or 60 years, I don't know what Bellman did in early days, but so this has been around for a long time. There was a tremendous step on the analytical side forward with the viscosity solutions, but the numerical treatment of HGB equation is a challenge still. And I think it's an interesting challenge because in working towards it, we develop concepts towards how to deal with curse of dimensionality. These HGB equations do not arise in optimal control, but that's definitely one very important situation where they appear. Anyway, a nonlinear RD, if you have a nonlinear HGB equation in dimension RD, and if you decide to approximate in each direction with n nodes, finite elements or finite difference, whatever is your favorite, then you have n to the d nodes, in addition to minimization. So you have exponential complexity. Now, before we get started with this, if we want to do some numerical concepts, we really should always, I always worry, is HGB worth the effort? Because we can linearize and compare to Riccati. And how is it different? One way it is really arising in practice pretty quickly is Riccati is linear. If it works, HGB is typically, of course, giving the optimal one. So there's a difference. Now a list of techniques which are utilized or which are investigated. Of course, there is always the possibility that you try to just solve it directly, but quickly above dimension 5, the curse of dimensionality is serious. Then interpolation from open loop data. People have contributed to it. I am going to show our way of attack based on interpolation. Training neural networks. We have a way and other people have a way. I'm going to talk on our approach to it. The main thing in these two topics is that we know about the HGB equation to get the feedback operator, but we are trying to avoid it, to solve it directly. We want to use alternatives to get the feedback operator. Of course, once we want to quantify how good our solution is, we compare towards HGB, or at least by pencil and paper. We cannot solve HGB in general. Of course, if you want to solve it, and we tried also in part to do that, then tensor techniques, tensor train techniques are very useful. I may not have time to speak much about them. But there are other choices. Taylor expansions, already in the 70s and 80s, they have been utilized. Hopf formulas, Max Plus algebra techniques, tree structure techniques. So there are for many different directions nowadays, people try to contribute towards solving these high-dimensional HGB equations. So if we decide to go ahead, then what is our aim? It is the development of feedback control laws for high-dimensional nonlinear dynamical systems by means of efficient, in part, data-driven approaches which guarantee robustness, and if possible, do it as quickly as possible. And if possible, also the control should be sparse. So if you have an expansion, many of the coefficients hopefully are zero in these expansions. So in lookup tables, we are quick to look up our response. Okay. So chapter 1, the data-driven approach towards trying to get feedback function. Now I am back to my original problem. I want a feedback solution for the optimal control. And data-driven approach means I need to create data. So I'm in state space, and I sample the state space of our ODE. You may think of this as initial conditions. And I take in the initial conditions, and I compute the value of the optimal control. Open loop, that's my optimization problem. I have a good optimizer from MATLAB or Scilab or whatever library you have available. In addition, I want also the gradient of this function. And you are saying, how do I get the gradient? Unless you already know in advance. But how do I get this gradient? Do I need to compute it numerically from this data? I want to sample, but I will sample very scarcely. So getting gradients seems not useful at the moment. So one thing is data. I create my data open loop. And then I decide I want a model for my value function. It's going to be, at this moment, a polynomial model of this type. Okay, I take a basis, I, and the parameters to be determined. And then I set up a regression. For the moment, just look at V. I created my data. This may be a Euclidean one. I created my data, V, and I write the mass matrix. First, phi, right? I have my basis. I evaluate this basis function at the initial conditions. I set up the mass matrix, and then I would determine my coefficients by regression. But there's more. Now I do this also for the gradients. Okay, I didn't write it down in detail, but you can imagine how it looks. Once we just get around this difficulty that I want to create data for the gradient. In addition, I want as few coefficients as possible. I want as few coefficients as possible because I need to evaluate this value function, and if at different points x. So this L1 functional enhances sparsity. Okay, if we take an L1 spot, I don't know whether you have followed the literature on optimization with non-differentiable functionals, but this functional here, compared to a quadratic, is much larger at the origin. So if theta is small, maybe it's too large altogether, it will be just set equal to 0. That's the sort of easy explanation for enhancing sparsity. So it prefers coefficients which are 0. If they're already small, just ignore them. And then once we have, on the basis of this lasso, this means lasso refers to the L1 part here, least absolute shrinkage and selection operator. Once we have solved this regression problem, we are going to close the loop. We have V. Now we can, excuse me if I do that, but now we can go back to this V. We stick in V theta here, and we can close the loop. But it means I have to evaluate the gradient of V along the trajectory. Okay, so that's what I'm doing. Then I'm going to, I have this, and now this is my optimal cost. I have this now, I evaluate, no problem anymore. But I have this problem with the gradients. But now we remember, or we recall from open loop control optimization, that if I look at this problem as an optimization problem with respect to U, it's optimality condition. It's first order necessary condition for a minimizer. If U is unconstrained, that's the way I've written it here, is the primal equation. This is just this equation. The so-called adjoint equation, which is nothing but the dual of this, the functional-analytic dual. So you integrate by parts, you get a minus P dot, you linearize, that's this thing here, okay. The boundary condition at infinity, and then the relationship between this adjoint and the control. So far, I have not given away the secret, how I get the gradients, but lo and behold, the gradient of the value function is nothing than running back the adjoint equation to the origin. This has a, why do I say running back? Because this has a terminal, this has a boundary condition at the other side, at infinity. This is initial condition for the original equation, a terminal condition for the adjoint equation. I run this back to 0, I evaluate, and I have already, okay, I have the gradient. So once in my data generation, where I need to solve the open loop problem, I, in this case, immediately get information on the gradient for free, because solving this, I have P, I have the gradient. So these data are available, and they are very useful in the tests we have run. In fact, before going to the tests, however, I should say one more thing. We have this polynomial model. And instead, I'm going to take functions which are separate. I take separable functions as basis functions. You may think of these functions as monomials with exponent bounded by ij. So the degree of the polynomial is ij. You be a Chebyshev, or monomials or Chebyshev polynomials, for example. And we are replacing our ansatz now. Instead of, I cannot take all of them. I'll just take index. I'll just take indices from an index calligraphic I. Now, for a moment, let me spend a moment on telling you how we choose this index set, or the choices of the index set. The first thing would be that we take all monomials up to a degree S. So if I'm thinking of the 2 dimensions, x1 and x2, and S is equal to 2, I take x1 square, I take x2 square, I take x1 times x2, but I also take x1 square, x2, because the total degree, the maximal degree is 2. Or I say the total degree, I sum all the exponents. Looking here, this corresponds to the tensor product situation. Before doing tensor training, basis elimination. The total degree, so this has exponential complexity, n to the d. This total degree only has combinatorial complexity. But we take really the hyperbolic cross. We take the product of the exponents of the monomials. This favors monomials which have high degree in one direction only, and the other degrees is smaller. And this only has polynomial complexity, logarithmic complexity. I don't give the formulas here, but the difference between tensor product before doing tensor reduction and hyperbolic cross is significant. We use hyperbolic cross index set with monomials or Chebyshev. And now let me give one numerical. So that's the end of the procedure. Now let me give an example. Cookersmail ODE of agents, NA agents running around in the plane with locations yi. I is the index of the agent. Each y has two coordinates, the x1 direction, the x2 direction, and velocities. And the nonlinearity becomes smaller if the locations of two agents are further apart, and smaller if they almost try to collide, or want to collide, right? So this is the Cookersmail model in agent dynamics with initial conditions xi and for the velocities wi. So we are on the next slide, we are going to have 20 agents, and each agent has two coordinates. So we have 40, and we have the location and their velocity. So it's on the next slide, there is a ODE of dimension 80. We don't want to go to the origin now. We want to go to what's called consensus manifold. I introduce the average of the velocities, and we want that the agents run in the same direction with the same velocities. Okay, so that's behind this cost functional. This is the cost functional, NA agents running with the same velocity in the same direction, and a little bit of cost for the control, the dogs who is after the sheep. Okay, so this is the thing. And the first, maybe let's go to the graphics first and then to the numbers. So each color is one of the 20 agents. And if you don't do anything, they disperse. Now we did an optimal control solver just to see how good our feedback control is. We don't put noise on it or anything. So this is truly the solution of the Cookersmail optimal control problem. They run in the same direction and approximately the same length. Okay. And now there is the feedback controller. All right. We utilized specification lambda is this one, and we used data from the velocities and the gradients. So that's the augmented ones with the gradients in the data. And you can see that they are doing fairly well. If we wouldn't specify it, then they almost coincide. But we want a scarce expansion. If we know the velocities in the cost, then we don't do as well. Okay, so even in spite of the fact that we are training with more data points, we don't do so well. So taking the gradients is very useful. This gives me also the opportunity to compare this slide on the top right and the bottom left. If you go back to the dynamical system and put noise on it, plus noise here, or here, additive noise, or noise anywhere else. If you do the open loop control, this completely fails, or it may completely fail. It's very easy to make it completely fail because your open loop control did not take into consideration the noise in the system. If, on the other hand, you do feedback and close the loop, if you add a noise to this equation and you have a feedback loop, then your formula is a feedback formula for the state. It can react to the noise, and we have tested this. It changes it a little bit, but not too much. Now to the numbers. Okay, the numbers, we use the hyperbolic cross with degree 4. This makes the cardinality of the index at 3,500. We had 20 Asians, I said. The dimension of the ODE system is 80 now. Now, with how many initial conditions do we train? We trained in the box -33 by 80 with training data, 50, 70, or 2,500. This is part of this slide of this data here. And we cannot compute the open loop. We compared error to the open loop problem. So we had to solve the open loop problem. We cannot solve on the infinite horizon. Our infinite horizon was really pain. Once we had trained, we had done the lasso regression, then we had to evaluate how good this feedback really is. So we tested this by evaluation on a sample initial conditions, 5,000. Okay. Now I give you the numbers for 50 training points and the cost in the L1 regression here. Where did I put the L1 regression? Lambda. This regression was 7.5, whatever this is, but we are going to compare to something which is smaller. So we get an error in L2, we get an error in H1. Before comparing, we cannot say whether this is good or bad, but at least it's not. It works. It's smaller than 1. It's smaller. Okay. And we have how many components are non-zero? Out of this 3,500, 400 are non-zero. It's really sparse. Next one is we are going to make the specification a little less. So we have more components in the expansion. At the same time, our error reduces. Thank you very much. It's going in the good direction. Next thing is, instead of I leave out the data which correspond to the gradient here. If I do that with the same number of sample points, the results are more or less useless. To get into the same neighborhood or as our errors used to be, I have to increase the sample points significantly. And I do this for the same specification. And then you can see we get errors in the same neighborhood, but at a much higher cost for the lasso regression computations. That was chapter 1. That's one approach to, I wouldn't say at all to eliminate the curse of dimensionality, no way, but to somehow loosen it a little bit, to meliorate it a little bit. I explain another technique next. Oops, I started that, so I have to be much faster, right? I'm going, okay, I explained too much. I can speed up. Neural network approach. All right. I start with the problem as before. To give some mathematical results, I work in a function space. Our interest is a feedback formula. I work in a box. Everything, the trajectories evolve in a box. I want to explain a learning technique. I want to learn the feedback operator. Instead of using, you say f of y. I'm looking for f in a space of function calligraphic H. I know one such function, namely the gradient of, namely the value functions. This is unpractical. I want to learn a whole function from one trajectory. It's useless. I need to use many initial conditions and then take the mean average over it. Or more mathematically formulated, I average over complete probability space. So we propose this as the learning problem for the function f. Okay. Oh, I should have written f again here. Sorry. For all f, no, f is here, and for all these trajectories. And they have this problem has a solution under reasonable assumptions. But still, I have a difficulty. How to choose f? I need to discretize f. And one possibility to discretize f are, of course, neural networks. Neural networks consist of a superposition of affine functions followed by an activation function. A superposition of such function followed by an activation function. Only the outermost layer, no activation function. So that's the neural network. And then when I finally studied a little bit about epsilon, about neural networks, it's always written, please use all the structure in the problem that you know. And I know very little about my feedback function, but I know f at 0 is 0. So at least that, right? So f at 0 is 0. We stick this in, right? Because if you evaluate x at 0, that's what we subtract. So without that, numerics were completely hopeless. Then we did it and quite reasonable. And now, of course, the next thing I replace, next thing we have to study, and I don't have the time here, approximation results. And then if you look up universal approximation theorems, they used to be at the time, and we did it only for the function, not for the derivatives, and no constraints on it. So we really had to work on universal approximation theorems to apply them in this context. And we justified what we were doing. And I jump over that. We justified the approach in the sense that if there exists a function which approaches the feedback function, if there exists a neural network which approximates the feedback function by epsilon, then we can approximate our whole optimization problem by a constant times epsilon. Without going to the details, I go to some numerical results. Okay. Okay, again, I cannot work on the whole time interval 0 infinity. Our infinity is time t sufficiently large. I use 8 layers in the neural network. Many times the activation function is just the ReLU function, 0x. We smoothed it. Then we added residual connections. They are very useful in practice. Not everybody talks about it. I'm almost sure that most of the black boxes have such residual connections, but in papers they are not always mentioned. And then we start. Okay, first thing, in the linear quadratic case, we have the exact feedback operator, namely by Riccati. That's what I did at the beginning. And we compared and it worked well. Fine, thank you very much. So we go to nonlinear problems. The first one we tested was van der Pol-like equation. This second order equation here, van der Pol-like, because we made it really nonlinear by and exploding, right? Cubic explodes, finite explodes. And then we got the following result for feedback control on the basis of neural networks. In the first plot, please look only at initial condition for the van der Pol. So these are y1 and y2 directions of the van der Pol equation after writing it as a first order system. We had initial conditions for the training set. These are the blue dots. There's no control yet. So what is the system doing without control? and the origin is unstable. So they all escape, but they escape in an interesting manner. They go to a manifold and then they escape along this manifold. All right, all right. Okay, now we did linear quadratic feedback. We linearized the nonlinear van der Pol, and the blue stuff is the same as on the left. Now the red stuff. Let's take an initial condition which was not trained. We are now testing it. We are testing with this initial condition our closed loop, and that's nice. This goes to the origin. This is nice. It goes to the origin. But if we go further away from the origin, which is here, they again go to this manifold, the Riccati closed loop, the Riccati optimal. They don't make it. Okay. So they're okay. Before going to the neural network, hopefully it's going to work, we are going to what control theorists or Regelungstechniker, what they call higher order Riccati. We tested that. Oh, that's an even bigger challenge to neural networks. And then finally we did our neural network feedback, and lo and behold, from not only the training points, the blue points, but also from the red points, they converge ever so nicely to this manifold, from which, and once they're on this manifold, now they'll go to the origin. Fine. And we did this for discretized PDEs with, I don't know, dimension 50 or something like that. I have 2 minutes before it's 5:0. Oh, it's easy. Well, it depends on which watch I look. I would just say one thing. Of course, neural networks are a typical thing to test these days because they are everywhere, right?
Karl, you have 5 minutes actually. You started late, so you can...
Okay, thank you. Okay, now I can take. Don't laugh. I have a lot of slides, but I can. Okay. Anyway, so I started to say neural networks. You know, I should say before it really worked, Daniel Walter was helping me. He was on the first slide. I mean, we had a lot of tuning of the optimization, of the parameters, of the number of layers, etc., etc. Right? There's a lot of tuning work, and it is not mentioned so much in the papers. But then you get to know the people who are utilizing them. I started to ask them, and they tell me, yeah, it takes a while before it works. And so I said, well, we have this fantastic learning formulation. But with respect to the discretization, I am not bound to use neural networks. Let me just use polynomials, or let me say separable ones, monomials, or Chebyshev. Let me just use these guys and stick them into an ansatz. For a capital D, it should be here. I should have capital D. And of course, the boundary conditions, I take out some of them at the origin is 0, derivative 0. All right. And I again look at the closed loop formula. I look at the adjoint equation. It has a linearization of this, so that's why I hash them. So before I show you the numerical results, I should say at least we need a lot of evaluation of this function here. And it's useful to do it wisely. Mr. Donato Vasquez has helped me to devise some graph theoretical techniques, how to quickly evaluate. Once we know that evaluate it's like lexicographical lookup tables, but to do it efficiently for the function and its derivative. And that's one thing. The other thing is network people or sampling people always say, okay, you are sampling, but can you generalize somewhat? And yeah, we have some theorems which say we can generalize in the neighborhood of an optimal trajectory. And then we proved some theorems, and then we test. Before showing you results, I can say polynomials compared to neural networks in this situation were very effective and much less demoralizing to the people who implemented and who run the codes. Okay, so now we are continuing other situations of HDB equations, but mostly with polynomials, and not always monomials, always Chebyshev or Legendre, depending on the situation. So let me just then close with one more model problem. We want to stabilize the solution of the Allen-Kahn PDE. That's a PDE with the cubic nonlinearity. Zero for Neumann boundary. Here it's written for dimension 1. For a Neumann boundary condition, 0 is a steady state, plus and minus 1 are steady states. 0 is unstable, and plus and minus 1 are stable. And we control in locations omega I, these are just small subsets omega I of the interval 0, 1. And the controllers are the amplitudes of these controllers. You may want to, I don't know, Allen-Kahn is in theoretical physics, for example, but it's also the Schlögl model. It comes up a lot, right? So it's somewhere in the middle, you are spraying your density by some controllers to make it small. Here we discretized the PD by Chebyshev spectral collocation by 19 degrees of freedom. So eventually we had a 19 order ODE here. Hyperbolic cross for the discretization of the HDB equation. We sampled for in the intervals -10 to 10. We trained with 5 training data. And what do you see on these 2 figures here? We specified again. Specification here is less, is more specification on the left, 10 to the 0.1, and here it's 10 to the -6. Less specification should give us better results. But what do we see here? We chose a problem where we could still do honest optimization. So on the left, you see really the optimal value. Here are the test points. Each red dot is a test point. And corresponding to this initial condition, you see the optimal value of the cost function. So let me choose this one here, just to the value here is a little below 1, okay? A little bit more, and this is the optimal value function, really the optimal for the original optimization. And here is the one based on feedback. It's a little larger. Here it was a little below 1, here's a little above 1. But it's not bad, right, compared to the optimal one. And here is, we tested for a lot of them. And with less classification, it does a good job. So on this second chapter, in this case, I learned that it was fun to play with neural networks, but I don't want to put all my money in one heap only. I have to look at other mesh-free discretizations. You can find these results in a list of papers, and there you find many more references to the other groups who are working on similar topics on this topic. With this, I thank you very much for your attention. It's a good time to stop. Thank you.
Great, thank you very much. Are there any questions from the group? Let me put on the camera. I think you might be able to see. I don't know, Karl, can you see the group?
I can see. No, but I could if I only. No, I see. No, I see. Muted. Yeah, I see. Oh, lots of people. Nice, thank you. I see lots of of course everybody muted, and no pictures.
Okay, well there's a microphone up here. So if anybody in the room would like to ask a question. or anybody online. I don't know, you'd have to maybe send me a message in the chat really quick and then I can unmute you. Otherwise, I'll ask my questions. Maybe I should start anyway. Thank you very much for this very interesting talk. I had a number of questions throughout. I guess the first, maybe easiest question would be more of an opinion. So you mentioned open loop and closed loop strategies. How would any of this relate to sort of model predictive control, where I would do open loop on a small interval and then adapt to what I see an open loop on another small interval and so on and so forth? Is there any relation between what you did and maybe MPC?
MPC, yeah, of course. I mean, in my group, we worked a lot on MPC. Yes, I mean, for the non-experts, maybe I quickly say what model predictive control is. Yeah. Model predictive control, you, instead of solving the original disoptimization problem from 0 to infinity, you solve on a very short time interval, open loop, you stop, you solve on the next time interval, you stop, and then you concatenate. Then we concatenate. So piece by piece, morceau par morceau. Okay, we do that. Well, of course, number one is model predictive control is not optimal. This is optimal. Number one. So I would imagine that I can get model predictive control to fail. I can get it to fail, for sure. Whereas this one is feedback. At this moment, this will not fail. I'm almost sure. But locally, it's better than open loop. Yeah? But I mean, here, once I compute it, once we have computed and really, hopefully, let me say, obtained our feedback operator, that's once and forever. It may be ever so difficult. It may take me, nobody has tried Navier-Stokes yet, but it may take me a month to get the feedback operator for Navier-Stokes. But once I have it, I can sell it, and then I have it.
Right. No, that's good.
A big lookup table. I go tables over tables, right? And if somebody offers me a state y of t, he doesn't tell me where it's from, right? It may be he doesn't know the time. He offers me a state, maybe error prone or whatever. I apply the operator I have on my disk, and that's it. Right. So I would say feedback model predictive MPC is in between. Is in between.
Great, thank you. Any questions? I have more questions, but maybe anybody here in the group or online? Okay, I was wondering if you could comment. Oh, Joey Hart has a question. Joe, let me just unmute you. No.
Yeah, can you hear me?
Yeah.
All right, very good. Thank you. Yeah, thank you for a really interesting talk. So my question is along the lines of dealing with parametric uncertainties. As I understand, most closed loop control is based on representing uncertainty in an initial condition. And that was sort of based on historically thinking about disturbances to the system that knock you off the trajectory and you're trying to get back. If you have uncertainty in parameters, say like parameters appearing in your differential equation, then kind of an optimal closed loop control is still suboptimal because it's based on approximate dynamics. So how do you think we should think about parametric uncertainty in the PDEs?
You mean this stuff? Or
Yeah,
maybe
sorry. Yeah, as an example, it could be, say, a velocity field, a diffusion coefficient, viscosity.
Or you have something like this. Yeah. Yeah, and the diffusion coefficient is very heterogeneous.
Yeah.
Yeah, I spent all morning talking to another new postdoc on that. Really, we are just working on it. I don't know. I do not know. I don't know whether somebody has combined feedback control and, okay, of course, there's a big community in open loop control under uncertainty. Yes. This is the uncertainty in the coefficients. And we can start, but this community, the contributions which I know have not combined with feedback. I'm sure there is something in the engineering literature, but in the math literature, I do not know. No, I don't. I'm not sure about the engineering. I would suspect it could be. I haven't checked. Honestly, I haven't checked. But under uncertainty, the feedback, I don't know. I want to work in this direction.
Yeah, I think it's an interesting direction. I just started thinking about this recently, and it seems to me like it's something that I'm not aware of a lot of work on, but it's a major problem with a lot of applications.
Well, if you can send me the literature you have found, I'm willing to share our literature. But
Okay.
that we found, but it's very little.
Yeah, it is very little.
But I must admit, we have only searched in the, say, mathematics and a little bit towards the electrical engineering or something like this, or engineering, but not honestly in the engineering literature. So, which needs to be checked, which I feel I have to check. But it's thank you for the question, because I wasn't sure whether it's really so important, because I found so little literature. So I don't know.
Yeah, I mean, I'm not a control expert, but I think there's a pretty broad class of problems. I've been thinking about it from the context of aerospace, where you have uncertainty in things like atmospheric properties, aerodynamic properties, and things are highly uncertain because it's expensive to run experiments to test them.
Yeah, if you think of the re-entry problem, right? Space shuttle re-entry or something, right?
Yeah, precisely.
Yeah, the controllers, we know the controllers. And it's, well, of course, the people know the density and know what's going on in the atmosphere, but the closer to the Earth they get, then more the perturbation there is. And it's not affine, the perturbation. The perturbation is bilinear if you're lucky, or worse. I don't know.
Thank you, Joe. I think maybe if you look into the stochastic control literature, of course, the dynamical systems there are, I don't want to say simpler, but if I have an SDE, right, then there are some, I mean, there's a whole community on stochastic control, right? And I think the challenge there is that even when you can get feedback in a stochastic control setting, at least for me personally, it's somewhat difficult to understand, what the control means, right? Because you have to sample from a stochastic process, and you get a control that's a sample of your feedback in a sense, right? But at least there are people who would say that they've looked at it, except in the case of this equation on this page would be like dy, and then f would be linear in y, and then there'd be some maybe Brownian motion, and then you would sort of try to control that system somehow, whether through the drift or the diffusion or from an additional term. That might be something that would help, at least to see what they do. It's usually very specific.
Yeah, I'm aware of the situation where there is some affine Gaussian noise.
Yeah.
And affine, typically white noise, but noise.
Yeah.
And then the HTP equation that I addressed becomes a parabolic equation, where
right, yeah. So the Feynman-Katz equation,
where the
will give you then
of the covariance of the noise appears at the diffusion coefficient. I'm aware of that. But I think Mr. Hart asked more about parameters in the dynamical system.
Yeah, it's more challenging.
In this situation, I don't know.
That's more challenging, it's true. I guess if I may ask one more question, I was curious about your choice of sampling at the end. If there's if you were doing things optimally, if you were just doing a uniform distribution on this hypercube, or if there's room for improvement.
There's room for improvement.
Yeah.
I know that I do not know.
Okay.
Sorry, I have nothing. I have nothing wise to mention. I have nothing wise except, okay, if I may take your time, right? I mean, this is the state space, right? So you're sampling like this. You see my dots.
Yeah.
But anyway, in this learning approach, the learning automatically occurs along all the trajectory. Okay, where was my learning problem? If you look at my learning problem, y of t appears all along because I replace u by the feedback. So I'm really learning not only from one trajectory, I'm learning from, from one initial condition. I'm learning for the whole trajectory. And therefore it may depend a lot, the sampling, on the dynamics of the ODE. If this is a decaying or a wave equations type. So, and we have taken into consideration the free dynamics when doing the sampling. So this would be now a more sophisticated answer. Yes, we look to some degree at the F. We said, okay, where do the free solutions, how do they behave? I mean, they go to zero, they escape, or something like that. Are they very scarce in the neighborhood of the origin, or are they space filling curves? And accordingly, we sample.
I see. Okay.
So that is that's more than nothing, but
that's more than that.
It is not really super sophisticated, and it has not been done systematically. I should say that.
Great.
We learn from it.
Yeah, got it. Okay, if there are no further questions, I'd like to thank Karl for taking the time today, for giving us a very interesting talk, and hope to maybe see you soon here in Oslo.
May happen, right? I wait for the good summer.
Yeah.
We can work all day and go jogging at night.
Correct. Yeah.
All right.
Okay. Thank you very much.
Thank you very much, Thomas. And thanks to the audience.
Okay.
Thank you.
Thank you.